Yes, welcome back. So in the previous topic or in the previous video, we have discussed about the introduction of the strain energy and about the strain energy and the uniaxial loading. How in the uniaxial loading, how we can able to identify the strain energy. So in this now we're going to discuss about the work done, how the work done can be able to identify on the internal strain energy. So we're going to discuss that is to find out how to find out or what are the equations that has been identified in order to find out the work done in an internal strain energy. So from the figure where you can able to see this, one is a sigma x along with the complementary energy and the strain energy, where the strain energy is nothing but along with this two axis is moving, that is sigma x. So it is a continuation of what the diagram what we have taken with an uniaxial loading along with the three axes. So we are going to consider along with the x axis, that is the three planes dx, dy and dz. So now we can able to see this the complementary energy versus the strain energy. So from the figure, the force is nothing but how again when the force is nothing but when you going to apply some load on the element. So automatically when the force that acts on the element, it increases linearly from 0 to until its maximum value. So whenever the load is acting, so always the load starts from 0 to its maximum level. Maximum level, that is the load which is acting on the element. So this is how the load is acting from 0 to the maximum level based on the complementary energy versus the strain energy. Again, strain energy is nothing but a stored energy where it can able to store the energy after the removal of load, whether it easily it can able to regain its shape or size because of the energy which has been stored. So now what we can able to do is hence the average force. What would be the average force is the on the element is equal to the half of. See, to find out the average force on the element will be half of summation of x into dy by dz. So dx, dy and dz are the three planes which is acting. So now based on this, therefore the work done can be by the above the force. What would be the work done based on the above the force is to find out the force is nothing but average force into deformed length. See here again the deformed length is nothing but change in length by original length. So deformed is after applying the load, what would be the initial length, and after applying the load what are the because of the deformation what the length has been changed, that length into the average force. To find out the average force is nothing but half into sx by dy by dz into summation of x into dx. So dx, dy, dz and the three planes which is acting on the stress, that is called as an sigma x, or we call it as an xx, and the summation of x. Now this is what the equation what is the formula based on the equation based on the formula what we got the equation. Now for a perfectly elastic body, the above work done is the internal strain energy. See, to find out the perfectly elastic body, what would be the work done for an internal strain energy? The notation for the internal strain energy, what we're going to take is du, small du. So the du is nothing but half of sigma x into dy by dz into summation of x into dx. So sigma x is nothing but an stresses, dx, dy and dz are the planes which is acting along with the sigma x is nothing but one plane which is acting in the uniaxial, and the summation of x is the stresses are for all the directions. Now we can able to or we can rewrite this equation as half into sigma x into, so I'm going to shift the summation of x to left side, and the dx, dy and dz I'm going to rearrange in the right side, or we can able to rewrite, or we can able to write that equation in directly. So the next is nothing but now when we going to again to rewrite this, so the du is nothing but an work done for the internal strain energy. Du indicates the work done for an internal strain energy. So that work done for an internal strain energy will be equal to half into sigma x into summation of x into dv. So the dv is nothing but an v indicates the volume of all the things. So volume of all the dx, dy and dz. So the du will be equal to half into sigma x into summation of x into dv. So instead of dx, dy, dz we have written as an dv. So where dv will be equal to dx, dy by dz, and where v is nothing but a particular volume of that uniaxial loading element, that is which we have been taken in the earlier uniaxial element. Now by rearranging the above equation what we got here in the equation 3, we can able to write that equation as u naught will be equal to du by dv will be equal to half into summation of x into sigma x into summation of x. So by rearranging, just we have been rearranged that the equation u naught will be equal to du by dv will be equal to half into sigma x into summation of x. So the equation 4 represents the what the equation 4 represents the elastic strain energy in elastic body per unit volume of the material is strain energy. So per unit volume we can able to find out per unit volume that the density u naught is, we can able to find out the density also. For this, by rearranging the equation we can able to find out along with the elastic body, even we can able to find out the density also. From Hooke's law for elastic bodies, it may be recalled that even for the Hooke's law, what the Hooke's law says that if the stress is directly proportional to strain within the elastic limit, that we can able to recalled also. So by recalling that, what we going to get is nothing but sigma will be equal to change in length by original length. That is what the capital E into strain minus summation of, that is change in length by original length. Now again by equating this u naught will be equal to du by dv will be equal to sigma x square by 2e will be equal to capital E into summation of x square by 2. By rearranging or by differentiating this equation, u will be equal to integral of volume, that is v will be equal to sigma x square by 2e into dv. So this is the what the final equation where we can able to identify the work done for an internal strain energy along with the density when the Hooke's law can be able to recalled, right? So this is what the equation you got. Now for a same case, in case of an it is an uniform cross section where we have taken a rectangular cross section. In case if it is in a uniform cross section where it is subjected at the ends of an equal and opposite forces for a magnitude. So what we can able to consider is, you see we can able to see this diagram for a same condition, but the condition is here uniform cross section. So where the L and the P and this is a cross sectional area. For this same equation, what we got is u will be equal to integral of volume to L sigma x square by 2e into dv, where sigma x, that is stress, will be equal to load by area, where dv will be equal to this elemental volume and a will be the area of the bar and L will be the length of the bar. So by integrating this same way, this case is for uniform cross section, that is what we consider as a rectangular cross section. Similarly for a uniform cross section, again we can able to write down u will be equal to integral 0 to L p square by 2 e a square a into dx. Now to find out that internal energy, u will be equal to p square L by 2 ae. A is nothing but an area and E is nothing but an modulus of Young's modulus or modulus of elasticity for the given conditions. So this is how we can able to identify for an equations for a rectangular cross section and a uniaxial loading along with the rectangular cross section, and for a uniform cross section by applying the uh, and even we can able to find out the density, and even we can able to identify the internal energy or work done based on this given conditions. So this is the two equations what we got from the derivation. So these equations for the in the next we're going to use for the numericals in order to find out the strain energy for the different conditions. Thank you.